Teacher Carlos Plain of Durham School states, "Absolutely. I went through my whole time on Earth engaging in unequivocal speculation of the universe. Also, finally, the speculation is being tried. I welcome that, since that is the way we push ahead. That is the manner by which we make progress in science." The James Webb Space Telescope is disturbing and amazing a proportion of what has been viewed as truth in cosmology for the new year. Another ultra-deep picture shows that we have various goofs in cosmology. The telescope, which ought to show us the essential stars of the universe, is developing into an enemy of the past viewpoint and may present to us a completely shocking science. Not all specialists are quailing in fear at the new realities. Other well-informed subject matter experts welcome the movements, since it has for quite a while been clear that something was the matter with our old hypothesis. The deviation in the appraisal of the movement speed of the universe alone ought to have shaken original discernment previously, yet bringing all that into account, they adhered to old speculations. The cosmic microwave background, CMB, radiation, considered the most settled light in the universe, was made something like 380,000 years after the Big Bang, precisely at the point when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Scientists call this association reionization, which made the universe transparent to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were managing another sort of radio-receiving antenna technology. This discovery was for a long time considered to be conceivably the most vigorous piece of evidence for the theory of the old Big Bang, earning Penzias and Wilson a Nobel Prize and an undeniable spot in the history of space science. The CMB most likely provides a perspective on the early universe with little temperature contrasts, giving major information about the circumstances not long after the Big Bang. Experts incorporated the CMB as a strong piece of the primary evaluations of the material universe to check the movement speed of the universe, among other things. The cosmologist Edwin Hubble had already settled this in the late 1920s, finding that distant galaxies retreat from us, and that their speed is related to their distance. Today, these observations are known as the Hubble law, or the Hubble constant. Hubble didn't have the advanced studying techniques available many years after the fact when the CMB was discovered, which led to recalculated expansion rates. These were all around lower than Hubble's original figure. Later, specialists recalculated the rate using Type I supernovae as standard candles, giving stable light that could be used as a reliable measuring point. The evaluations within the CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while estimates using galactic impacts yielded around 74 kilometers per second per megaparsec. What does this disparity in determining the expansion speed of the universe really tell us? Did you know that this goof has been known since the 1990s? Since that point, experts have known, or at least suspected, that something might be wrong with the assessment of the CMB, the assessment techniques, or the plausibility of the universe's expansion. The irregularity between the observed and anticipated values of the expansion rate is referred to in science as the SAA strain or Hubble strain. The repercussions of this strain are significant, showing that essential pieces of how we understand the universe might be flawed. For quite a while, subject matter experts were confused, but since the James Webb Space Telescope went online, it has equipped specialists with dazzling data that may now uncover information on the issue of the expansion speed of the universe, with systems so old and mature that their expansion should have begun theoretically before the Big Bang, disturbing old cosmology. Investigators no longer talk about mistakes or assessment contrasts. They talk about the crisis in modern astronomy. Not only could the expansion rate be off, but the whole idea of expansion, or the Big Bang itself, is being raised into question. Images from the telescope provide evidence of a universe totally surprising from what we have long thought. The SAA pressure was the main challenge to experts who still believed in old theories. Now, they face an issue. Do we truly understand the universe? Various analysts stand on the remnants of their once brilliant source of both revelation and torture, exploring space with dread and grappling with what they find. Considering the crisis in science, we ought to ask ourselves, what do we actually know about the universe? To genuinely answer this, we need to understand how science functions. Speculative scientists use a complex arrangement of numerical models, careful data, and brilliant thinking to move from the general to the particular. Their understanding comes from a mix of insightful credits, critical results, and speculative evaluations. The term theory alone shows that these are hypotheses and ideas, not absolute facts. The primary basic data we have are the images telescopes provide, the sound waves and radiation gathered with radio telescopes, and the latest data from neutrino focus systems or gravitational wave markers. With the James Webb Space Telescope, we now have an instrument that can split light into individual frequencies and analyze it in astonishing ways. Webb can show us the fundamental pieces of galaxies in the early universe, billions of years ago. How much mass they contained, the number of stars present, and even the shape and course of a galaxy's evolution. Webb, however, has limits. For instance, it can't always definitively determine whether we are seeing galaxies or black holes with immense gravitational forces that shine as brightly as a galaxy. We must face the truth that our science has long accepted a limited number of possible outcomes as facts while dismissing alternative explanations. Research has, for quite some time, been certain of its accuracy. The latest discoveries from the James Webb Space Telescope are significant indicators to replace theories with new insights, as has happened globally in science. Investigators are eagerly awaiting the new revelations, which are unexpectedly astounding, and many experts are trying to develop new explanations. The new discoveries shake the foundation of old theories. The underpinnings of our science are upsetting a large number of experts. The ongoing models of genuine science are still generally established on Isaac Newton's regulations from the 17th century. His laws of movement and gravity were the groundwork of our understanding of the reality of this world and the universe for quite a while. Newton's standards describe the development of objects under ordinary circumstances and functions, especially on Earth. However, in space, his speculations required advancement, mostly finished by Albert Einstein in the mid-20th century. Einstein's unique theory of relativity, published in 1905, changed how we interpreted reality, showing that events are relative to one another and depend upon the observer's movement. His general theory of relativity, published in 1915, expanded this idea with mathematical representations of gravitational qualities based on the curve of spacetime by masses like stars or galaxies. Einstein's principles and ideas were significant in many areas. However, he too recognized their limitations. He knew his theory would never completely describe the universe and longed to see a unified theory, which he never achieved. No other expert has reached this stage either. Wouldn't it be interesting to know where it lies? Michio Kaku, an astrophysicist from the USA, said in an interview that addressing this issue would certainly win a Nobel Prize. Might we one day investigate whether the specialists could have missed potential misinterpretations or whether our telescopes are to be blamed? Dark matter and dark energy are at the top of the suspect list for the critical explanations behind the cosmological crisis. Our developing models of the universe integrate ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been clearly observed, and their confirmed presence has never been demonstrated. They likely exist in some form or shape, requiring alternative explanations for the universe's development and the elements of galaxies. On the other hand, they could have properties we don't yet understand. One idea is that the actual properties of dark matter and dark energy have changed over time, possibly showing some sort of evolution. Gravity is another theory to be tested. This force, which creates attraction through mass or the bending of spacetime, has not yet been fully understood. The concepts of spacetime, which originate from Einstein and have been widely maintained, may require revisiting. We can't rule out the possibility that gravity has surprising properties or that another force is responsible for the gravitational attraction between objects over time. A few constants have been established in cosmology and astronomy as general principles. The study of the universe has always been a journey defined by our constant pursuit of understanding and discovery. From ancient human civilizations observing the stars to modern space telescopes investigating the depths of the universe, each step toward improving theory and observation has revealed new secrets while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, remains a beacon of our scientific progress, promising to change how we interpret the universe's beginnings and development. Launched with remarkable capabilities, JWST represents a leap forward in observational space science, designed to look deeper into the universe than ever before with extraordinary precision in analyzing radiation. The cosmic microwave background, CMB, often referred to as the glow of the Big Bang, offers a perspective on the universe as it existed shortly after its first interaction with the world. This ancient form of radiation conveys central information about the universe's initial conditions, including its temperature variations, which are pivotal to understanding the development of galaxies and large-scale structures. The uniqueness in the determined values of the Hubble constant, known as the Hubble strain, has been a subject of ongoing debate. It suggests that something is amiss with our fundamental understanding of the universe and its early designs. Discoveries challenge conventional theories and require a reassessment of whether our perspective on cosmic expansion is generally flawed. New insights could uncover hidden pieces of the universe's creation, raising questions about dark matter and dark energy, two unexplained elements that make up most of reality. The progress of science relies on the ability to reshape our theories in light of new data. Webb's central mission embodies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and should shed light on new perspectives on the universe's secrets. The fate of cosmology could witness enormous changes, leading to significant implications for how we interpret the universe, from the Big Bang to the ongoing processes that define its fate. The answers to the greatest and most profound questions might lie beyond our current knowledge and capabilities. Observations may ultimately be essential in uncovering new insights that could reshape how we interpret reality itself. The way forward for cosmology and space science is filled with potential. Each novel observation and clue from telescopes like Webb brings us closer to answering the fundamental questions humanity has ever asked. How did the universe start? What is its ultimate destiny? Are there other forms of life out there? Or are we alone in this vast universe? These are questions that may one day find answers, and the James Webb Space Telescope is at the very forefront of this grand effort. The future of cosmology will likely involve a combination of new technologies, refined theories, and groundbreaking discoveries that continue to push the boundaries of what we know. As we venture further into the unknown, one thing is certain. Science, like the universe itself, is always in a state of constant evolution, driven by the quest for knowledge, revelation, and the miracle of discovery.